Hopefully the last couple people get here real soon so they can do what we're doing today. As I said yesterday, today we're going to be doing Desmos activity to practice the chi-square test for goodness of fit and the things that we have to do to conduct one of those tests. And we'll not be having you do an entire like 4-step process today in Desmos. That just takes a lot of time. But we will be doing the different components and finding like expected values, finding it the chi-square statistic, finding a p-value, making a conclusion, writing hypotheses, and things like that. So we'll do all the parts, which is what I think we need to practice. All right, so I'm going to share the link for the activity in the chat. All right, well, if you haven't joined the activity yet, please do so shortly. We're going to be getting started here. Thank you for those of you who've already joined and are ready to start. You might want to have a piece of scratch paper available, and you're also probably going to want to have a calculator available at some point to do these exercises. All right, and so kind of in how we've done this previously, the first few slides here will be kind of review of the things that we've seen from yesterday's lesson. All right, so the chi-square test for goodness of fit allows us to test a claim about a distribution of categorical data. This is different than the previous inference methods we've used because it allows for testing the evidence for or against an entire distribution rather than just one value within the distribution. So rather than testing each value in a categorical distribution against an alternative, which would be very time consuming, we can test the whole distribution with the chi-square test for goodness of fit. That's the kind of big idea here. The next screen we have our formula for the chi-square statistic. You might need that today. All right, chi-square statistic is a measure of how far the observed counts are from the expected counts, and the formula for the statistic is given below, right, where the sum is over all possible values of the categorical variable. Again, I apologize for how small some of this text turned out. We have our chi-square distributions. Chi-square distributions are a family of density curves that take only non-negative values and are skewed to the right. A particular chi-square distribution is specified by giving its degrees of freedom. The chi-square test for goodness of fit uses the chi-square distribution with degrees of freedom equaling the number of categories. All right, and so we have a couple of models of different density curves for the different degrees of freedom here in the chi-square distribution. Things to remember: as the degrees of freedom increase, the density curves become less skewed and larger values become more probable. The mean for its particular chi-square distribution is equal to its degree of freedom, and for degrees of freedom greater than 2, the mode or the peak of the chi-square density curve is at degrees of freedom minus 2, whatever the degrees of freedom for that distribution is. All right. We have our conditions for performing chi-square test for goodness of fit. That is our random and 10% condition, which are the same as the random and 10% conditions we've seen previously. And then we have our new large counts condition. This is saying that all expected counts, right, for all of our categories within our categorical variable are at least 5. Then we have the chi-square test for goodness of fit. This is kind of in a nutshell, how we go through this process, right? We check our conditions and suppose the conditions are met to determine whether a categorical variable has a specified distribution in the population of interest, expressed as the proportion of individuals falling into each possible category. We perform a test of the null hypothesis that the stated distribution of the categorical variable in the population of interest is correct, versus the alternative where the stated distribution of the categorical variable in the population of interest is not correct. We start by finding the expected count for each category, assuming that the null hypothesis is true. Then calculate the chi-square statistic. down below, observed minus expected squared divided by expected, add up all those for each category, where the sum is over the k different categories. K is just a placeholder for the number of categories. The p-value is the area to the right of the chi-squared under the density curve of the chi-square distribution with k minus 1 degrees of freedom. Right, so like all the other significance tests we've done, right, we have our hypotheses, we check our conditions, we do a calculation, right? In this case, we have an extra step in our calculation process, so to say, in that we have to find our expected counts. We should already have observed numbers. We find the expected count. Then we can do this chi-squared calculation. We use that to find a p-value, which we then compare to some significance level alpha to help make our conclusion. Right. Is there any questions about any of these things that are in the review slides? So then that brings us to the first thing for you guys to work on. Right, so here's our first problem, computing expected counts. Jenny made a 6-sided die in ceramics class and rolled it 60 times to test if each side was equally likely to show up on top. Assuming that her die is fair, calculate the expected counts for each possible outcome. So you'll just type in this middle column here, what you believe the expected count is. If you get that correct, it will tell you it's correct. If it is incorrect, it will tell you that it is not correct. Right, so this will automatically give you feedback based on your responses that should help you troubleshoot if you have problems. Right, so we'll give you all just a couple minutes to do this one, and then we will talk about it. All right. So please, if you're in the activity, please do the activity. I see some of you guys are logged into the activity, but you are not doing the activity. You're not going to get the benefit of doing this if you don't participate. We need to practice these things. All right. So it does look like there's a few of you who have figured this out and you have all the correct responses. First, we're not specifically told what the probability of rolling each side of that die is. What in our context tells us the probability? Someone tell me what in the context tells us the chances of each side showing up on top for our null hypothesis, so to say, the assumption.
Since it's a 6-sided die that's fair, it means each side has an equally likely chance of coming up, so it's a 1 in 6 chance.
Exactly. Thank you, Devin. That is exactly right. We are told that we get to assume that her die is fair. It's a 6-sided fair dice in our assumption, in our null hypothesis, right, so to say. So that means the 60 rolls should be split equally among all the sides. So we just divide 60 by 6, or 60 times 1/6, and we get 10 as the expected count for each side. Okay. So even though we weren't told exactly like what the different proportions were, as we saw in some of the examples yesterday, we have enough information in the context to know what to do. Is there anything I can clarify about that? Right. Awesome. So then we'll move on to the next one. The next one is again computing expected counts. This time we do not have equally likely events. So a company claims that each batch of its deluxe mixed nuts contain 52% cashews, 27% almonds, 13% macadamia nuts, and 8% Brazil nuts. To test this claim, a quality control inspector takes a random sample of 150 nuts from the latest batch. Calculate the expected counts for each type of nut. Again, this will automatically check your responses to tell you if they are correct or incorrect. Also remember, for an expected count, it's okay to have a decimal. We do not need all these results to be whole numbers. Decimals are okay. Right, so we'll give you all a couple minutes to calculate this one, and then we will talk about it. All right. So looks like we got a few people who have sorted this one out. A couple people who are still working through it. More people have it correct. And someone who has all of these verified correct, can you tell me how you calculated the expected count?
For each of them, I multiplied the total, like, amount of nuts times the probability. So for cashews, I did 150 times 0.25, or 0.52.
Mm-hmm. Exactly. Right, so this is very similar to when we were calculating expected values with random variables. Right, sample size times the probability of that thing happening. Same idea applies here. We have our sample size, 150 nuts, times the proposed distribution proportion, right? So we get 150 times 0.52, 150 times 0.27, 150 times 0.13, and 150 times 0.08. Please make sure you're putting your decimals in the right places when you're converting your percentages to decimal form. Otherwise, you're going to get some weird answers. All right, thank you, Devin. So ultimately we get, make sure I'm typing it, 78 here, 40.5 for almonds, 19.5 for macadamias, and 12 for the Brazil nuts. Right, the other thing you should do, just make sure you didn't make a calculation error, is make sure that when you add these things up, it should add up to 150. We should be able to account for all of the sampled nuts. Right. Next. All right, so using the same context, and we'll use the same context for the next few problems, right? We want to state appropriate hypotheses for performing a test of the company's claim. Right, so you may want to refer back to the 6th screen in this set of slides to look at the two rough examples on how to write our hypotheses and write the null and alternative hypothesis for this claim. For this one, we'll give you a few minutes, and then again, we'll discuss it. All right, so let's talk about this one. Some of you guys look like you're on the right track, and some of you look like you're really not entirely grasping the hypotheses yet. So the first thing, when we're trying to write these hypotheses, the first thing you should do is know what is the company's claim, right? Because the company's claim will end up being the null hypothesis, right? Their claim is that this is the distribution of the nuts. If you look at the shared screen, I've highlighted part of the context, right? The company has a claim that each batch of its deluxe mixed nuts contains 52% cashews, 27% almonds, 13% macadamia nuts, and 8% Brazil nuts. That is their claim. We want to test if that is true, right? So the null hypothesis is that their claim is correct. So again, if you're looking at the shared screen, we can type in our null hypothesis, right? You can say the company's claim and just paste in their claim and then correct. All right, so the companies claim that each batch of its deluxe mixed nuts contains different amounts is correct. Right, we could also say, as one of your classmates did, the stated distribution, the company's stated distribution of its deluxe mixed nuts is correct. Right, we can kind of shorten it up a little bit. But essentially, we're saying their claim is correct. Then the alternative hypothesis here we just take the entire null hypothesis, copy it, paste it, and add the word not in between is incorrect. Right? The alternative is just saying that some part of that is not correct. So if some part is not correct, the whole thing is not correct. Right? So the companies claim that each batch of its deluxe mixed nuts contains 52% cashews, 27% almonds, 13% macadamia nuts, and 8% Brazil nuts is not correct. And that's it. Kind of the template you can use for these is just taking whatever the claim is in your context and copying it. And for the null hypothesis saying that it is correct, and for the alternative saying that it is not correct. All right. Is there anything I can clarify for this or provide more detail on? Right. Writing these things as statements is going to be the easiest way to do this. If you're going to use parameters like P cashews, P almonds, P macadamia, P Brazil nuts, you have to make sure to define that parameter in some sentence later, saying, you know, P sub type of nut is the true proportion for that, you know, type of nut in the mix. Right? You have to have that extra thing. All right, go to the next part. So next, we have a company that claims that each batch of its deluxe mixed nuts contains 52% cashews, 27%, same context again. Use the table below to calculate the chi-squared statistic for the distribution. Right, so we have our observed and our expected counts in our table here. You will type just the chi-squared statistic value in this entry window. You do not need to put the whole calculation. You do not need to put chi-squared equals. I just want the number. And round this number to 3 decimal places. Right? We don't want to keep the whole decimal, but we don't want to round off too much. Okay. So you'll probably want to go back to, if you don't remember the formula, screen 3 has the formula for calculating our chi-squared statistic. All right, let's see. And again, this is set up to show you whether or not your response is correct. I believe if I did this right. Yep. All right, so it needs to be within a certain set of values to be considered correct here if I have the code done properly. Hopefully it works. All right. So the responses that I see being submitted, which there's only 3 people who have submitted responses, that's okay, are correct, right? They're looking good. Ultimately, this ends up being 6.5 0.99, or some rounding thereof. So again, we have our 4 different categories, right? Cashew, almond, macadamia, Brazil. We calculate a fraction, like a value for each of those, which is a measure of how far away they are from the expected value. So for instance, the value from cashews is 83 minus 78 squared divided by 78. We get 29 minus 40.5 squared divided by 40.5. 20 minus 19.5 squared divided by 19.5. 18 minus 12 squared divided by 12. All right. And so ultimately, I believe this should be. Can you guys see the calculator on the screen?
Yes.
Okay, good. I forgot whether or not I shared the screen or just the window, so good. Okay, so let's make this a little bigger. So we see in the calculator, it can be very nice if you can type these things in the way that you would write them, per se, right? Write it as big fraction, add them all up, we get 6.59876, blah, 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 blah. Make sure you're rounding correctly. If you round this down to 2 decimal places and you round it to 6.59, right, technically that's an incorrect rounding if you're rounding to 2 decimal places. If you're rounding this to 2 decimal places, the number to the right of the second decimal place is 8. That's larger than 5. That's 5 or more. That means you round up. That would round this entire thing to 6.6. Okay, so make sure you're using your rounding rules properly. If you do not know how to make a fraction on your TI-84 calculator, you will hit alpha and then y equals and then enter. And you get your little fraction that you can fill in. That makes things a little bit easier to make sure things are done the way that you want them done, possibly when you're calculating stuff. Right. Also, if your result is a fraction and you entered in fractions to do your math, that should pop out as a fraction. So that's always nice too. Is there anything I can clarify about calculating our chi-square statistic? All right. Let's get that next one. Large counts in degrees of freedom, same context. We need to confirm that the expected counts are large enough to use a chi-square distribution to calculate the p-value. So answer is the large counts condition met, yes or no, then submit that answer. The submit button that's to the right of the second question is the submit button for yes or no. And then what degrees of freedom should you use? Type in just the number value for your degrees of freedom and hit submit. It will tell you whether or not you've got the correct responses. All right, let's take a couple minutes and answer these 2 short questions. All right, so those of you who answered the first question, is the large counts condition met? You got it correct, it is yes. All right, we have at least 5 in all of the expected counts in our table, right? If we look back here, all the expected counts are at least 5. That's the large counts condition in this case. So it has been met. Our degrees of freedom, right? We have 4 categories of nuts, right? Cashew, almond, macadamia, and Brazil. That means our degree of freedom that we will use for our chi-square distribution is 3. 4 minus 1. Right? Remember, the degrees of freedom for a chi-square statistic or a chi-square distribution is the number of categories minus 1. It is not having anything to do with our sample size, which is how we determine degrees of freedom for estimating means, right, in our t distribution. Right, this is number of categories. So anything I can clarify here? Or do you have any questions? So moving on to our next part here, same exact context here with our deluxe mixed nuts. Now that conditions have been met, you have the value of the test statistic, 6.599, and you know the degrees of freedom, 3. Use table C to find the range of the p-value, and you have a link right here to the formulas and tables in Canvas. Table C is the last table in that PDF. All right, so find the range of the p-value. Just like when we use table B to find a p-value, we're not going to land exactly on a value here, so we'll have a upper and lower bound for our p-value based on table C. Then based on that p-value, what conclusion would you draw about the company's claim distribution for its deluxe mixed nuts? Justify your answer. Remember that since a significance value has not been given, you should use alpha equals 0.05. And we're going to give y'all 5 minutes to work through this part, and then we shall discuss. All right, excellent. So some really good work here for those of you who are submitting answers. Looks like everyone I've seen so far has good stuff here. All right, so table C works very similarly to table B. Right, if we go into our formulas and tables here, go all the way to the end for table C. Right, we have our degrees of freedom 3, right, and 6.599 will fall between 6.25 and 7.81. That means that we then follow this up to our tail probability across the top here, which is our p-value, and our p-value is between 0.1 and 0.05. Now, when we write this out, it's proper to write it as the p-value being between 0.05 and 0.1 because 0.05 is smaller than 0.1. I did see that some of you use the calculator function for this, the chi-square CDF, and if you did that, I believe you got 0.0858, which is also absolutely okay to do. So if you know how to do it that way, that's fine. You will get a more exact answer. However, remember, regardless of the method you use, you should get enough using table C, definitely using the calculator, to answer the question about, to essentially get a conclusion related to the significance level. Both should give you the same conclusion. If they don't, then something probably went wrong somewhere. All right. Right, and we can type this in a number of different ways. Right. If we're going off of table C, we get a range of values. We'll have 0.05 is less than the p-value, which is less than 0.10. And we can make that look pretty. Right. You could also just type that the p-value is between 0.05 and 0.1. Right. And that is enough for this here. Right. You would also, on like an AP exam, want to mention that these values were attained from table C. If we use the calculator functionality, you need to show that that's what you used. Right. And then our conclusion, our p-value is greater than alpha. It's greater than 0.05 because it says our p-value is greater than 0.05. So we failed to reject the null hypothesis. This means we do not have sufficient evidence to say that the company's claim is incorrect. All right. Is there any questions about this step in our process here? All right, so then the last thing we're going to talk about is our follow-up analysis. Right, this was mentioned yesterday. I told you we'd see it today as far as what it is. So when sample data lead to a statistically significant result, which was not the case in our example we just did, all right, we can conclude that our variable has a distribution different from the one stated. When this happens, start by examining which categories of the variable show large deviations between the observed and expected counts. Then look at the individual terms, observed minus expected squared divided by expected, that are being added together to produce the test statistic chi-squared. These components show which terms contribute most to the chi-square statistic, and therefore contributing most to the results that we had. Right, determining which component contributed the most to the chi-square statistic will allow us to get an idea of which categories have incorrect hypothesized values. So that's the follow-up analysis. Right? It's just basically saying, okay, well, what contributed the most to the results that we just got? And we'll go to this last screen here. I do not need you guys to actually answer this question. I'm just going to talk about it. So this is a sample follow-up analysis. In the example that we saw in class yesterday about the birthdays of NHL players, we found that the results were significant and that there is evidence against the distribution of NHL players' birthdays being evenly distributed throughout the year. The table below shows the comparison between the observed and expected counts and the values for the individual terms from the test statistic for each category. All right, and so which component contributed the most to our chi-square statistic? In this case, it's fairly obvious because it's larger, more than 2 times larger than the next closest one, and that is this January through March component. Right, it has the largest contribution to the chi-square statistic, and it has the largest difference between observed and expected. All right. This then can allow you to make a secondary statement or a secondary conclusion, right? In the case of this particular study, the author wanted to find evidence saying that players born earlier in the year had an advantage and that they had a better probability of going on to the NHL later in their career. This result supports that claim, so to say, from that author. This result shows evidence that those players born earlier in the year, January through March, have an advantage. So we can make kind of a secondary follow-up conclusion outside of just the conclusion of like, well, this distribution is different. It's not evenly distributed. Right, so that's our follow-up analysis. We can only do that, though, when we find significant results. Is there anything I can clarify about this? All right. Stop sharing my screen there. All right, so that brings us to the end of the activity. Essentially the end of the lesson for today. I have the practice problems ready to go in Canvas for section 11.1. So if you would like some more practice with these things, or you think you would benefit from more practice with these things, please look at the practice problems. I do not have the solutions yet, but those will be up soonish. If you have any other questions, comments, concerns, anything you need help with, please make sure to let me know. You're more than welcome to stick around at the end of this session to ask questions or get help. Otherwise, send me a message, email, come to office hours on Monday, get the help you need. I hope you guys have a great rest of your day and a wonderful weekend, and I will see you all next week.